is we often want to know what vectors a transformation maps to the zero vector. It's important for understanding the structure of our transformation in a way that we won't talk about right now. But it's a set of vectors that map to zero. Well, what do you think the solution to this is? I can tell you just by looking at it, and you will in a minute, that the only solution is x, y, both zeros. Certainly that's a solution, it always is, right? But it's the only solution. Why? Well, because this matrix is invertible. All right, with all the signs. It's 13, and we observe, if we look carefully, that 13 is not 0. Everybody believe that? Okay? Well, by what I said before, and you might have forgotten it because I'm saying these things kind of fast. So this matrix is invertible, right? Well, we don't have to invert it. We just write out the equation without bothering to invert the matrix. Since the matrix is invertible, we know we've got an inverse matrix. And whatever that inverse matrix is, when we multiply it by 0, 0, we're going to get 0, 0, right? So the only solution is a zero matrix. Very simple. So if you're asked to solve an equation where a matrix equals 0, 0, first thing you do is you calculate its determinant to see if the matrix is invertible. You don't go to the trouble of inverting it. You just calculate its determinant. If the determinant isn't 0, then maybe, well, if the determinant isn't 0, you can invert the matrix, and your only solution is a zero vector. If the determinant is 0, then there might be, and very possibly are, and generally will be, other solutions. Matter of fact, there'll always be other solutions, okay? Now, so if we want to solve one where the determinant is 0, what do we do?